Good morning. All right. So we're going to pick up where we left off. We finished up 3.1 last week. I know it's been a while. So we're going to pick up with 3.2 today. Just a couple of reminders about homeworks that are coming up. The 3.1 and 3.2, because I think we should be able to finish 3.2 today. I've moved that homework to Wednesday of this week. So you've got until Wednesday night at midnight to get that one done. If we don't quite finish it up today, then we'll definitely finish it on Wednesday. So I'd still like to have that one due on Wednesday, but I think you'll probably have everything you need by the end of the day to finish that one. Okay. The 3.3 and 3.4 right now, I've just got it Friday. It'll probably get moved into next week. I just want to see how far we get by the end of the week, and then I'll adjust that date. Okay. So I think upcoming dates at this point. Any questions, comments, concerns before we get started today? All right. The other thing, I did grade your test over the break, and so just go in there, look at my feedback. Right, all you have to do is click on the submission, whatever you submitted, and you can actually see my comments there and how many points you lost for each question, that kind of thing. If there's any discrepancies, right, if the points don't add up right or something like that, let me know. Or if you have questions in general about how I graded something, let me know that too. Feel free to drop in during student hours. That's a good time to ask questions about that. Or if you just want to email me any questions, we can talk about it there. Okay. All right. So let's take a look here at 3.2. Okay, so 3.2 is polynomial functions and their graphs. So we've talked about polynomials in general. Now we're going to look at what a polynomial function looks like when it's graphed, and the different things that the function itself can tell you about its graph. Right? So in general, a polynomial function of degree n is going to look like this form right here. Okay, so again, just remember that all of these a values right here are just going to be numbers. Okay, so those are your coefficients of your polynomial. X in this case is going to be the variable, and then we have all of our exponents. Okay, n is going to be the highest exponent, and then we have this n minus 1, which again is just another exponent. This will be to the first power down here, and then you're going to have a term that's just a number that has no variable on it at all, and that's what we call our constant or constant coefficient. Okay. Now, in general, some terms that I might be using as we go through this, leading coefficient is going to be whatever the coefficient is of your highest exponent term. So in this case, a sub n, this term right here, is going to be your leading coefficient. And then if we're talking about the entire leading term, then we're looking at the entire a sub n x to the n. So everything including the leading coefficient and the variable and the exponent, that's all the leading term now. And the reason we're going to use that, that's going to actually tell us something about the graph of these by just looking at that leading coefficient. And so we're going to use that a lot. So I'll be using that term some. Any questions about just the general form of a polynomial function now, or what any of these terms mean? Okay. And so here's an example of just a few different types of polynomials. Okay, so our first one here, we got p of x equals 4x minus 7. So if we're talking about the degree of this polynomial, remember we're looking at the highest exponent on your variable. In this case, we have an x to the first power, so our degree is just going to be 1. The entire leading term then is going to be the 4x, right? Because the leading coefficient will be the 4 itself. The leading term is the entire term, so 4x. And then the constant in this case is just the minus 7. Okay, and so we're going to call that a negative 7. Always keep signs with their values, right? So in this case, that minus 7 becomes a negative 7 if we're talking about the constant term. And the next polynomial here, we've got x squared plus x. The degree, we look at the highest exponent on your variable. That's a 2. Therefore, the degree is 2 here. Leading term then is x squared. Constant term in this case, because there is no constant, right? All of our terms have variables. We would say that our constant term is 0 because we could just put a plus 0 there at the end. And then our next one, 2x cubed minus 6x squared plus 10. Again, the degree is your highest exponent, so our degree is 3. Leading term is 2x cubed. Constant in this case is the 10. And then our last one, the degree is 4 because that's our highest exponent. Leading term is the negative 5x to the fourth. And then our constant is going to be a negative 2 because, again, we're going to keep that sign with the number. Any questions about identifying the degree, the leading term, or the constant for any of these polynomials now? All right. Skipping that one. In behavior. Okay, so this is why we need to understand what the leading term is, okay, and what our degree is, because that's what's going to help us to figure out what our in behavior of our polynomial is going to look like. And I know this is really small on the screen. You can see the slides right there in the course content section. So if you need to download it so you can enlarge this and see it a little bit bigger, that's fine. Okay, so first thing we're going to do is look at the degree, okay, because that's going to separate us into two different categories. If P has an odd degree, right? So if our degree is an odd number, then we know that the end behavior is going to look like one of these two graphs. In both cases, the ends are going in opposite directions. So it's either going to go down and to the left, up and to the right, or it's going to go up to the left and down to the right. The way we're going to determine which one of those it is by looking at our leading coefficient. If the leading coefficient is a positive value, then it's going to look like that graph on the left. Okay, so it's going to go down to the left and up to the right. If the leading coefficient is a negative value instead, then it's going to look like this graph where it's going up to the left and down to the right. Now, in terms of actually describing in behavior, we have to talk about what the x and y values are doing. Okay, so I'm going to look at this first one and say, well, as x approaches negative infinity, that means we're looking at the left-hand side of our graph now. What is the y value approaching in that case? So on that first graph, as x goes to negative infinity, what direction is y going? Towards negative infinity also, right? So it's going down, and so we're going to say that's approaching negative infinity. Now we're going to have to look at the other side of our graph. So as x approaches positive infinity, what's happening to the y values? Okay, they're going to infinity, right? Because all we really care about is to the far right-hand side of this graph, what's happening to those y values. So as x goes towards infinity to the right, the y value is going up towards positive infinity also, right? So this is y approaches positive infinity. Okay, so that's how we would describe the end behavior of that first graph now. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y also goes to positive infinity. Any questions about that description there for end behavior? And now the dotted lines in the middle mean absolutely nothing, okay? Because depending on what the degree is of this polynomial, that thing could go up and down several times, right? We don't know exactly what the middle part of the graph looks like. All we're saying now is if the degree is odd and the leading coefficient is positive, we know that that's the end behavior, what's happening to the left and the right of that polynomial now. Okay, let's look at the next graph. So again, I want to try to describe this. I'm going to look as x approaches negative infinity first. So for that second graph, as x goes to negative infinity, what's happening to the y values? It's going towards positive infinity, right? So we would say y approaches positive infinity. And as x goes towards positive infinity, as we go to the right, what's happening to the y values this time? They're going towards negative infinity. Good. And so that's how we would describe the end behavior for that second graph. Any questions on the two graphs where the degree is odd? Okay. Now we have to look at what happens if the degree is even instead. Well, in this case, notice both of these graphs, the end behavior is going in the same direction, right? So either both of our ends are going up or both of our ends are going down. The way we're going to determine that is by looking at the leading coefficient now. If that leading coefficient is positive, then we're going to get something that looks like that first graph. And if the leading coefficient is a negative, then it's going to look like this other graph down here. So again, let's think about our end behavior. As x approaches negative infinity, what's happening to the y values? Okay, so looking at that third graph now, as I go to the left towards negative infinity, which direction are the y values going? They're going up towards positive infinity, right? So we would say as x goes to negative infinity, y approaches positive infinity. If we're thinking about the y values, if they're going up, they're going towards positive infinity. Any questions about that in behavior? Okay, what about when x goes towards positive infinity then? What's the y value doing? Also positive infinity, right? Because we just said that both ends are going in the same direction this time, so both of them are going towards positive infinity. Okay, so now let's look at the leading coefficient being negative. As x approaches negative infinity, what's happening to my y values this time? Going towards negative infinity, right? Because the left-hand side of that graph is going down, so the y values are going towards negative infinity. And as x approaches positive infinity, so as I go to the right, what's happening to the y values this time? Also negative infinity, right? Because again, we just said if the degree is even, then both ends are going in the same direction. In this case, with a negative leading coefficient, both ends are going towards negative infinity. So those are the four cases now, right? So when we look at a polynomial, we're going to look at the degree to determine are the ends going in opposite directions or the same direction. Then we're going to look at that leading coefficient and decide is it positive or negative, and that's going to tell us specifically which direction those ends are going. Any questions on the end behaviors there? All right, let's look at some actual polynomials now. Sorry, example 2. All right, so we want to determine the end behavior of this polynomial. All right, so what's the first thing we have to look at to decide which category we're going to be in, based off that last slide? We look at the degree. Good. So if we look at the degree this time, what's the degree of this polynomial? 4, right? Now, all we care about is whether that degree is even or odd. So do we have an even degree or an odd degree this time? This one's even. So 4 is an even number, which tells us that our ends are going to do what? Are they going in opposite directions or the same direction? Same direction, right? So anytime you have an even degree, the ends are going in the same direction. So we know they're either both going up or both going down now. Now we're going to look at our leading coefficient. What's the leading coefficient this time? Negative, just the -2, right? So we don't have to worry about the variable in this case. If we're just looking at leading coefficient, it's just the number out front. And so that's going to be -2. Now, in this case, all we care about is whether that's a positive value or a negative value. So what do we have this time? Good. This time it's a negative. And so what does that tell us about both ends of this polynomial then? They're going down, right? So towards negative infinity. And so now we can describe this end behavior. We have an even degree, which means they're going in the same direction. Negative leading coefficient means they're both going down. So we can say as x approaches negative infinity, y is also approaching negative infinity because it needs to go down. And as x goes towards positive infinity to the right, we know both ends are going in the same direction, so y is also approaching negative infinity. Okay, so if you think about this graph now, again, we don't know exactly what's happening in the middle, but I know the left-hand side is going down this way. I know the right-hand side is going down this way. And then in between, right, it could be doing whatever. And eventually we're going to get to the point where we can describe exactly what's happening in between also. But for right now, we're just worried about the end behaviors. Both ends are going in the same direction, and they're both going down. Any questions about that one? All right. Let's take a look at this one now. Okay, it's the same thing. We're just trying to determine the end behavior. And then we're going to look at just the graph of 3x to the fifth just to show that it actually has the same end behavior as the graph of the polynomial that's given up top. All right, so again, first thing we're going to look for is what? Degree. Good. What's our degree this time? This time it's 5, right? That's our highest exponent. Is 5 even or odd? This time it's odd. We have an odd degree. So what does that tell us about the ends of our polynomial then? Opposite directions. Good. So I know both ends this time are going to be going in opposite directions. All right. Now let's take a look at our leading coefficient. I'm just going to abbreviate it LC. So what's our leading coefficient this time? 3. Again, at this point, we care about whether that's even or odd, or sorry, positive or negative. Okay, so is that a positive or a negative value? That one's positive, right? So we have a positive leading coefficient. So now we just have to think about, in this case, we already know they're going in opposite directions. So with a positive leading coefficient now, as x approaches negative infinity, what's happening to the y value? Okay, so you have to think back to that those first graphs that we looked at. With a positive leading coefficient, odd degree, as x goes to negative infinity, what was y doing? That goes towards positive infinity. Good. Well, hang on. Let's go back. There you go. Okay, so we're looking in this case, we have an odd degree, we have a positive leading coefficient, right? So that's that first graph. So as x goes towards negative infinity, what was happening to the y value? That one's going towards negative infinity, right? So we're looking at this first graph right here. That's our example. Okay, so if we do this, we say as x goes to negative infinity, y also goes to negative infinity. And then as we go to the right, as x goes towards positive infinity, what should happen to the y value there? Yeah, this time that should be positive infinity because we know that both ends are going in opposite directions. Okay. Any questions about how we found that end behavior for this one now? All right, I'm going to switch over to Desmos real quick. I'm going to graph that polynomial, and I'm going to graph just 3x to the fifth because they want us to verify that they have the same end behavior here. So our polynomial was 3x to the fifth minus 5x to the third plus 2x. Okay. And so if you look at that, we said as x goes to negative infinity, y should be going to negative infinity. Okay, so that's our left-hand side of our graph down here, right? And you can see this is going towards negative infinity towards the left. And then as we go towards positive infinity on the x, it says our y value should be going towards positive infinity. And you can see in this case that they are. They're going up towards positive infinity this way. Now, just to verify, if we were just to graph 3x to the fifth, notice that should have the same degree and same leading coefficient, right? So all the other terms don't matter in this case if we're just talking about end behavior. And you can see this blue graph, same thing. As I go to the left, it's going towards negative infinity. As I go to the right, it's also going towards positive infinity. So those other terms in this case only affect, all those little turns in between, but the end behavior is completely decided by just that leading term, okay? Just the degree and the leading coefficient. Any questions about that now? All right. All right, real zeros of polynomials. Okay, so if P is a polynomial and C is a real number, the following statements are all equivalent. Okay, and this is going to be useful because that means if we know that one of these things is true, we know the other three also have to be true. Okay, so saying that C is a zero of P is equivalent to saying that X equals C is a solution of the equation P of X equals 0, which is the same thing as saying that X minus C has to be a factor of P of X, which is also the same as saying that C is an x-intercept of the graph of P. So again, if you know any one of those four things, then you know the other three also have to be true. We're going to come back to this, right? Because I'm going to go through some examples now where we actually know certain things, and we're going to try to use those to prove the other ones, okay? Now, intermediate value theorem. If P is a polynomial function, P of A and P of B have opposite signs, then there has to be at least one value of C between A and B where P of C is equal to 0. And there's a lot going on there, right? A lot of different variables. So let's break this down, and I'm going to graph this, right? Show you a picture of what this is actually saying now. So if we were to sketch this, what would it mean for P of A and P of B to have opposite signs, right? So think about, first off, what do P of A and P of B represent? What types of values on our graph? Okay, so in this case, what would be the X values? The thing here, our polynomial function would be like P of X. So which variables would actually represent X values this time? The A and B would be your X values, right? So in this case, we have an A and we have a B. Those would be along the X axis. So I'm just going to pick two random spots here, A and B, right? It doesn't matter where you put them. A needs to be less than B. That's just how we're going to define these all the time. Okay, but in this case, right, as long as you got A and B along the X, which means that P of A and P of B are what types of values then? Those are your Y values, right? Because if we substitute A and B into the polynomial, that's going to give us a corresponding Y value for our graph. So in this case, we know that P of A and P of B have to have opposite signs, meaning that one of them needs to be positive, one of them needs to be negative. It doesn't matter which is which, right? So long as one is positive, one's negative. So I'm just going to put P of A up here, and I'm going to put P of B down here. So we have an A and B value. Those are the X's. And then along our y-axis, we have some P of A and P of B that have to have opposite signs. Now, if we're thinking about this, what this means is that A, P of A, there's going to be a point on your graph, and at B, P of B, there's going to be a point on your graph. Now, this says that there has to be at least one value C somewhere between A and B. So is C going to be an X value or a Y value? C is an X value, right? So somewhere between A and B, sorry. There's going to be some C value, right? It doesn't have to be exactly halfway, just somewhere between those two values, where P of C is equal to 0. So what does that mean? That the Y value is 0 there, right? So at C, the Y value is 0, which means we're going to have a point right on the x-axis. In other words, there has to be an x-intercept somewhere between A and B if the y values of those 2 points are opposite signs. Because our polynomial then, if it connects those 2 points, it's going to have to pass through the x-axis somewhere between A and B. So that's what our intermediate value theorem tells us now, is that if you have P of A and P of B with opposite signs, A and B as your X values, there's going to be a point somewhere between A and B where your graph has to cross over the X-axis. Okay? Any questions about that intermediate value theorem now? All right. Example 4. Okay, we want to sketch the graph of this polynomial function. Okay, so they give us a factored form, x plus 2, x minus 1 times x minus 3. All right, now, if we know the factors of this polynomial, let's think back to that slide that told us all the equivalent statements. If that's true, right, if we know that x minus c is a factor, right, because we've got 3 different factors here, that also means that the c value has to be a 0 of the polynomial, that x equals c has to be a solution of the equation p of x equals 0, and that c has to be an x-intercept of the graph. So what we can do now is we can take each one of those factors, we can set them each equal to 0, and that's going to tell us where our x-intercepts are for this graph. So since it's already in factored form, all we have to do is take each one of our factors, set them equal to 0. So x plus 2 equals 0, x minus 1 equals 0, and x minus 3 equals 0. Then we just solve each one of those. So if we solve that first one, what's x going to be equal to? Good. So x equals negative 2. What's our second one going to be? Positive 1. And the last one would be positive 3. Good. Okay, so again, because those are the factors of our polynomial, by setting them equal to 0, that gives us our x-intercepts for that polynomial now. Now we want to try to sketch the graph of this polynomial function. So the other thing we would need in addition to those x-intercepts is the end behavior, right? Well, let's think about what the end behavior would be for this one. What's the degree of this polynomial going to be? Good, because if I multiply all this out, right, I have an x times an x times an x, that would give us an x cubed as the highest exponent, right? So we know our leading term this time, if I were to actually multiply all this out, would be x to the third power. And it would just be 1x to the third because there's no numbers in front of those x's. So it would just be an x times an x times an x. It would give us 1x cubed. So our leading, or sorry, let's look at the degree. The degree this time then is 3, which means we have what type of degree? Odd, right? And again, that tells us then our ends are going in opposite directions. Now let's look at the leading coefficient. What's our leading coefficient this time? It's an understood 1. Good. Again, all I care about there is whether it's positive or negative. So do we have a positive or negative this time? Good. So now let's think about the end behavior. I'm going to describe that this way. As x goes towards negative infinity, y is approaching what? Negative infinity, right? This is like that last example that we did. And as x approaches positive infinity, y should be approaching what? Positive infinity. Good. So again, that's just odd degree, opposite directions, positive leading coefficient tells us the left-hand side's going down, right-hand side's going up. So now let's see if we can get a sketch of what this graph might look like then. So first thing I'm going to do is I'm going to go ahead and put my x-intercepts on the graph. So along the x-axis now, I'm going to plot a point at -2. I know that's one place we should cross the x-axis. I'm going to put a point at +1. That's another x-intercept. And then I'm going to put one at +3. That's my last x-intercept. Now I'm going to look at my end behavior. Well, I know to the left, the graph should be going down. So over here, I'm going to have something that looks like this. And on the right-hand side, it should be going up. So I'm going to have something that looks like this right here. Now I just have to connect everything and make sure that I'm passing through those x-intercepts. Now I still don't know exactly how high or low this graph's going to go, right? That's just kind of a guess thing at this point. And we'll talk specifically about how to find those highest and lowest points later. But for right now, I'm going to take my graph. I'm going to go through this x-intercept here. I need to pass back through this x-intercept right here. And then it needs to go back through this x-intercept and connect my end behaviors that way. So again, just by knowing the end behavior and the x-intercepts, we can get at least a decent idea of what this graph's going to look like. And again, the only thing we don't quite know for sure yet is how high and low those middle parts are going to go. Any questions about that one now? Okay, so in this case, if I were to actually multiply all this stuff out, right? Let's try to do it real quick. Foiling the first two would give us x squared minus x plus 2x. So that would be plus x and then -2 times x minus 3. And then I would need to actually distribute all of this out. When I do that, that first term is going to be x times x squared. And so that's going to give us x cubed, right? And you could keep going to find all the other terms, but that's what tells me that that leading term has to be x to the third power, and that's why the degree is going to be 3 this time. Does that answer your question, Jonathan? Good. So again, it's because it's an x times an x times an x, right? That's what tells us that we're going to have x to the third power. Any other questions on this one? All right. Let's take a look at this one now. So same thing, we want to find the zeros, which are those x-intercepts, and then we're going to sketch the graph of the polynomial. So what's the first thing we're going to need to do here if we want to find those zeros? Think about those 4 equivalent statements. Okay, we can describe the end behavior if you want to do that first, right? So what's the end behavior going to look like this time? So if we have a degree of 3 and a leading coefficient of 1, that looks very familiar, right? That's the exact same thing we had on the last one. So our end behavior should be as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. Okay, so same end behavior as the last example, right? Because that leading term is exactly the same. It's x cubed again. All right, now let's talk about the zeros. How can we find the zeros this time? We have to factor, good, because remember, if c is a zero of our polynomial, that means that x minus c has to be a factor. So if we can find those factors, set those factors equal to zero, that's going to give us our zeros, which are also the x-intercepts of our graph, right? That's why it's so important to recognize all 4 of these statements mean the same thing. So if you're looking for zeros, you're really just looking for x-intercepts, okay? Which means we need our factors. So how are we going to factor this one? Good. We have a common factor of x, so let's go ahead and pull that out. So if we bring out the x, we're left with x squared minus 2x minus 3. And now we look at the trinomial in parentheses. Can we factor that any further? Okay, and so what would those factors be? Okay, good. Right, so we look at the x squared, right? That's going to give us an x times x. The only factors of 3 are 3 and 1. Then it's just a matter of getting our signs right. Okay, we need a negative 3, which means the signs need to be opposites. And we want a negative 2x. So I'm going to make the 3 the negative, and I'm going to make the 1 the positive. So minus 3 and plus 1. Any questions about the factors this time? All right, now that we have our factors, what are we going to do? Good. Set each factor equal to 0. So we're going to have x equals 0. That's our first one. X minus 3 equals 0. And x plus 1 equals 0. Well, x equals 0 is already solved, right? Nothing to do with that one. What's the next factor going to give us? Good, positive 3. And the last one's going to give us negative 1. So now we know the zeros of our polynomial are 0, 3, and negative 1. Those are also the x-intercepts of our graph, right? So now when we go to sketch the graph, those zeros are going to tell us where we cross the x-axis. So I'm going to start here with 0. That means we have a point at the origin. Positive 3, 1, 2, 3 gives us a point over here. And then negative 1 right in here. End behavior is just like the last one. So to the left, we're going down. To the right, we're going up. And then we just need to connect and make sure we pass through each of our x-intercepts. Go up like this, come down like this, and then go up and connect to that end behavior there. Again, I still don't know exactly how high or low the graph goes, right? We're going to get to that point. But for right now, as long as you can recognize which direction the ends are going and where it crosses the x-axis, right, that gives us a lot of good information about what the graph's going to look like. Any questions on that one now? So again, if you're ever given a polynomial like this, the first thing, if you're looking for zeros or x-intercepts, you got to factor first, so you can set each one of those factors equal to 0. All right, let's take a look at this one now. So we're given negative 2x to the fourth minus x cubed plus 3x squared. Again, we want to find the zeros and then try to sketch our graph. So what do you want to do first here? Okay, good. So what are we going to do to factor this one? Okay, good. We have a common factor of x squared this time, so let's bring that out. It's going to leave us with negative 2x squared minus x plus 3. Okay, so now we look at the trinomial, see if we can factor that further. So what factors would give us negative 2x squared minus x plus 3? Okay, almost. Okay, so the problem is we need a negative 2x squared in the front here. And so we know we're going to have a negative 2x and a positive x. We also know we need a positive 3 at the end, which means those signs have to be the same. So it's actually going to be negative 2x and positive x here. Then we need a 3 and a 1. 3 is going to have to go here and 1's going to have to go here. And then I'm going to use two positives so that I get a negative 2x on the outside and a, sorry, I did that wrong. The negative is actually going to need to go with the x instead. So I'm going to put the negative here. That way I get a positive 2x and a negative 3x, and that's going to actually give us what we need there as a negative x in the middle. Okay, so just pay attention in this case to the fact that we need a negative 2x squared, so there has to be a negative on either the 2x or the x, and then the signs of the 3 need to be the same, so I'm going to use two positives here to make that happen. Any questions about how I got those factors? All right, now, once we have our factors, we're going to do what? Good, set each one equal to 0. So we've got x squared equals 0, 2x plus 3 equals 0, and negative x plus 1 equals 0. How are we going to solve the x squared equals 0? Take the square root. Good. So if we take the square root of both sides here, x equals what? Still 0, right? Okay, so even if you did a plus or minus, right, positive 0, negative 0, doesn't matter. It's still 0. So x just equals 0. Now let's solve this next one. So the first thing I'm going to do is move the 3. So I have 2x equals negative 3. Divide by 2 this time. So x equals what? Good. Negative 1.5 or negative 3 halves. Right? Either way you want to think about it. Okay, but when we go to graph it, right, it's going to be between negative 1 and negative 2. In this last one here, the easiest way to solve it is just to add the x to the other side. That's going to give us 1 equals x, or x equals 1. Okay, so now we know all the zeros. What's the other thing we're going to need to think about here if we're going to sketch this graph? The end behavior. Good. So if we look at the leading term, what's our degree this time? Good. We have a degree of 4. It's an even value. That means same direction. Leading coefficient is what? Negative 2, which means we have a negative. And so they're both going to be going which direction this time? Down. Good. So because it's an even degree, we know they're going in the same direction. Because it's a negative leading coefficient, that means both ends are going down. So let's go to sketch this now. Go ahead and put my x-intercepts on there first. So my zeros were x equals 0, which is the origin. X equals negative 3 halves, so that's negative 1.5. So between negative 1 and negative 2. And then finally, x equals positive 1 will be right here. In behavior, we know both ends are going down. I'm going to have this end going down like this, and this end going down like this. All right, now, here's what I want you to think about. If I try to connect these and I actually pass through all of my x-intercepts, am I going to be able to connect my ends if I do that? It's not going to work, right? Because if I go up, I'm just going to kind of show you what I mean by that. If I go up like this, and then I come through this one, and then I go back through that one, I'm not going to be able to connect my end. Okay, and these are the only x-intercepts of my graph, right? So I can't pass back through the x-axis somewhere, right? Because those are the only places it should cross. So what that tells me then is that one of these x-intercepts, my graph is just going to bounce off of that intercept instead, so that I can then connect my end behaviors. Now, the one that's going to bounce is this one right here. And the reason I know that is because of this x squared right here. Okay? And we're going to talk about specifically what we're looking for, but it's because that x happens twice, because there's an x squared there, that it's actually going to bounce off of that point instead of passing through it. And then I can pass through the next one and actually connect my end behavior. So it's going to come up like this. It's going to come down to this one, but bounce. And then it's going to go down through that one and then connect over to that end behavior. All right, that's not very smooth. So something like that, okay? And again, that's just a rough sketch. I still don't know exactly how high those middle points go or anything, okay? But to be able to connect the end behaviors and to actually have x-intercepts at all of those locations, the only way this works is that because that x squared tells us that x happens twice, we actually have to bounce off of that point instead of actually passing through that point. Okay. Now, here's the rules for that. If we have what's called an odd multiplicity, okay, meaning that zero happens an odd number of times, then it's going to pass through the point. And notice here, though, it kind of levels out at that point rather than going straight through it. Okay, because this says if m is bigger than 1. If m is equal to 1, it just goes straight through. Okay, so that's what we've been looking at before. But if it happens an odd number of times, like 3 times, 5 times, 7 times, then it's still going to pass through, but it levels out at the point instead. Okay? If m is even, and again, greater than 1, then it's going to bounce at that point instead. And that's what we just saw in the last ones, because we had an x squared. That x happened 2 times. That's an even multiplicity. Therefore, it bounces off the graph at that point instead. So basically, we just look at our exponent. We decide, is that happening an even number of times or an odd number of times? And that's going to tell us whether the graph bounces off the x-axis at that point or whether it passes through the x-axis at that point. Now, that's where we're going to stop for today, and we'll come back on Wednesday and actually do some examples with the multiplicity so that you can see exactly what that would look like in the polynomial itself and then what the graphs would look like. Okay? We'll stop there. Again, work on the homework, right? Because the 3.1, 3.2, I've got that due Wednesday at this point. And then once we get through that, then we'll get into 3.3 hopefully on Wednesday and wrap that up, later this week or early next week so that you can get that homework done. Okay. Again, let me know if you've got questions about any of the test grades or anything like that. Come see me during student hours if you need to. Have a great afternoon, and I will see you all on Wednesday.